So if you remember last time, we almost finished up chapter 22 on the randomization test. And basically what the randomization test is making the null hypothesis that nothing is going on, that whatever effect you see is just due to chance variation. In this case, homework and final scores are completely uncorrelated. Nothing's going, this correlation, observed sample correlation we got was just due to chance variation, the luck of the draw. Randomizations tests make that come alive. They reenact that scenario. They say, okay, if your null is that in this population, let me just make sure it looks better, that in this group, this wider population that you took this sample of 107 students from, homework and finals are completely unrelated, completely and utterly unrelated. You have a scatter plot that looks like this, total random, right, between homework and finals. This is your null. That R in this entire population of thousands of students, R in the population, equals 0. R is your correlation coefficient, the absolute value of it. It's the same as little r, except it's always positive. So what does that mean? It means that the correlation is 0. That's kind of crazy if you think about it. Homework is related to finals, right? But this is the null. And the alternative is saying, that it's not 0 inside here, and that's the reason you got your sample R of this. You got almost 0.4 in your sample, okay? So we're taking that seriously, but we're not doing it from a wider population. We're not randomly drawing from that. We can with our data program. We do that. In fact, you're going to be getting samples from a wider population. We did confidence intervals. You all got random samples from a wider population. We reenacted that. But usually, when you do these, you don't know this wider population. And in fact, we didn't in this case, because those 107 students were a self-contained class. They were not randomly chosen from a wider population of stat to 100 students. So there's another way we can visualize it, and that is actually creating our own experimental random draws. So what does that mean? It means that we, just by the luck of the draw, if they look like this, if the 100, what's the chance? Okay, so what's the chance that we would see this strong a correlation? So what are we going to do? We're going to take all 107 scores and just scramble them and compute the correlation coefficient that you get. We'll do it over and over and over again and compute all the R's we get and look at the sampling distribution under the null of those R's. So just to refresh your memory, because some people keep having a difficulty with this hypothesis test, what we've been doing before is imagining this bigger population and then randomly taking 107 points out of there, and what we got was this correlation. Let's say we got this where we did see some positive correlation. But what the null says is that we just happened to pick points that had that strong a correlation. That's what it says. We just happened to pick those. And if we did it again, we might get a negative correlation. We might get there's going to be a range just by the luck of the draw. And the probability distribution of that, of those draws, of that range of correlation coefficients follows the normal distribution, or a t distribution. Okay? That's the idea. And here, I mean, that's if we let it be negative or positive. And here, we're just going to get the empirical sampling distribution, so we did that. And these are just the positives. So if we got a negative, we're just as likely to get negative, right? So if we got a negative 0.1, we change it. We're just looking at the absolute values. So this was the empirical sampling distribution of R under our simulated simulation of that random variation, of that probability model, of just scrambling, assigning. So if it was you, you would just be randomly assign somebody else's final score that would be attached to your homework score. You don't think those are correlated. Most of them aren't. So we're asking, okay, how likely is it that in our actual class, that if the null was true, we'd see a correlation coefficient as big as this is our observed sample R that we got right here. And our observed sample R, and it's equal to what? What is this equal to? This is equal to that. This is, see where it's coming in at? Right here. It's 0.3926. That's our observed sample R. And we're saying, we're imagining, we're testing this null hypothesis that it was like, if the null's true, how likely is it that it would, that it was just due to random luck that we got such a big correlation, that we happened to just pick out the points that just were so strongly correlated. And you can see it's very, very unlikely, beyond a reasonable doubt. And why this is, and then we looked at 1,000 R's, and we did, didn't we, when we did this, we did get a tiny little bit of a correlation. Not a tiny bit of a correlation. We finally got one sample that was out there. Here, I think we got 0. Right? That's where we left off. Does everybody understand that? Okay. So right here again, let's just match it up. And this is what we have right here. It's our observed sample R. Okay, so now let's move on. And R is the same thing as little r. Which is equal to the absolute value of little r. Okay, so now let's move on and look at multiple regression. And this is where we left off, and let's just do the same thing. So now what are we doing here? So how we're going to, we have 3, okay, so now we have homework, exams, predicting finals. So now we have 3 sets of numbers, and our sample R was, this is a really big sample R. And why is it looking like this? This is annoying. Let me just check this out. Isn't it, there's so much glare. I think this, you really like this better. Does it look good to you? From my point of view, it looks a lot of glare. Do you mind if I switch it? It's bothering me. So I'm just going to switch it back to here. That's easier for me to see. Okay. All right. So now what are we doing? So we've got these 3 variables here. So we can't really draw a scatter plot anymore. So what I want you to imagine is when we're doing this probability model here, what are we doing? Maybe we could put all your scores in a cube, in a box, because we're in 3D now. And this is the equation for a plane. And we actually got this regression equation. This is our least squares equation for predicting finals from our homework and exams. And we got it based on the actual finals right here. This is your actual finals. And what? Your actual finals and your actual homework and exams. All right. So now what are we going to do? So now what we're going to do is keep these actual homeworks and exams and just randomly assign you somebody else's final, right? And see, just do just create this box model. Under the null, we're saying that this correlation coefficient of 0.6198 is just due to the luck of the draw. It seems pretty ludicrous, right? It's kind of crazy. That's all we're doing. So what are we going to do? We're going to say, okay, how likely is it that we get such a big R just by the luck of the draw, and how would we enact that? And this is the part that's really, you have to think about creating an analogous creating a real random draw so that we can figure out the sampling distribution of that. We can look at that. And instead of relying on our usual central limit theorem and all the stuff that we've been doing and just pretending, imagining this wider population and then base it on these known statistics of assuming certain assumptions about the distribution, we're saying, hey, we're going to create our own model from a real population. It's so cool. It's really easy. It's really great to think about because it's so simple, right? So let's do it. So what would we do? Well, one way to think about it is you're in 3D, so you could like shake up all the points and imagine in 3D that you're at your, okay, so you have, here's your homework, and here's your exams, right? And you take these actual points, so everybody has like this person got a 30 on the homework, and a 60 here, and somebody else maybe got almost an 80 and an 80, so it'll be way up here. And, there's just, you plot all these points, and they have some kind of correlation here. These are just the homework and the exams. But now we're in 3D, so we have to have another axis, so we'd have a final going up like this, just y-axis of the final. And what we're doing is we're just saying those are, those heights those are just going to be randomly assigned from here, randomly. So, for example, I'll just randomly pretend, we shook all these up, and we just randomly, or if we had a box, imagine these just being shaken up and down. You just randomly assign these to different people. And then we're looking for the best fitting plane. We'll come up with another regression equation. We'll do the least squares. We'll get a different regression equation, least squares, and it will be the best fitting plane through those random points, right? And then from that, we compute an R. How well does that plane predict our scrambled finals? So, for example, let's just do it. Pretend I scramble these up, and then, okay, 68 is the randomly assigned final given to this person. And I'll do it again, just pretend, okay, so let's say this person got a 60. Instead of the actual 52 they got, instead of the actual 62, etc. And I do that all the way down here to the very end, and then I get, what I'm going to be doing is instead of computing the, so what I'll do is I'm going to be using these scrambled finals. So let's do this. So here's what I did originally. I took these, right? These, let's say these are your x1 and x2. These right here. Those are your actual ones. And I'm predicting your actual finals. That's what we did. That's our sample so far. And we got a very strong prediction. We got 0.6198. Now, what am I doing? Okay, so let's just write that down. So these are the actual points. So the actual, let's call this x1, x2, and y. All right? Now, what am I doing? I'm taking these, and I'm pairing them up, trying to predict these random y's. So these are the same actual x for each of you. Keep your same homework and exam scores. And now I'm trying to predict, I'm pretending that I'm trying to predict these random y's. Right? So, imagine putting all the final scores inside a box. That's what we just did. And then randomly choosing one and assigning it to student one. Then randomly choosing the next final. And that would be assigned to student 2, etc. Then we'd compute we'd get a new regression equation here, a new one that would make predictions, right? And then we'd compute R between these random ones and these ones, and the predicted final scores based on the model that fits them best, the new regression equation that we get here. We'd get a different one, and then we just say, okay, how close are we to predicting a random thing, right? And so we do this. Let's say we did that 1,000 times. Then we have 1,000 R's, each computed from 107 real homework and exam pairs, predicting these scrambled finals, and then we can make a histogram of that, the empirical histogram of that, and that's what we did. That's what we can do. Let's go to the computer and do it. All right, and what we're going to do before let's just be clear here, we are going to be comparing what? This observed R, that's our observed R right here. This is our observed sample R, right? This one right here, I put it right there. This, our observed sample R, and see how likely it could be just due to random chance. All statistical procedures are based on, all our methods, everything you learn is based on some probability model. What is it trying to do? It's trying to assess what's due to random variation and what's due to something else. Like, is there some signal there? And every single one of these tests is just trying to look at how likely it is that our result could have been due to random variation. We're just trying to separate out the random noise, the stuff you see just due to random variation, and the stuff that's really due to some other cause. That's what it's all about, right? We're trying to separate out those two things. So in everything, whenever you're doing any kind of statistical inference, you have to sort of imagine, okay, how can I translate this situation, whatever the situation I'm in, into one where, how can I model it so that I can model the chance part of it? And so I can get some kind of distribution for the random element, and then I can say, okay, that part is random, and how much, that's what this stuff is, that's random, and okay, if I'm in this range, well, then I might not be able to distinguish, I might not have a signal, but I'm way out here, and you say, whoa, I got a signal. This is not, look at all that distance there. This is not random variation. And what's really nice about the randomizations test is you create them. You actually look at you don't have to worry about assumptions or anything. You know, when you make an analogous model like this, when you do a simulation, you know exactly what you're doing. You know how close that model is to what your real situation is. Does it make sense or not? And then you just program the computer to do the computing part, and you use your brain to do the statistics part. And the statistics part is matching up real-life situations to these, to models, right? I mean, boy, it's really exciting stuff that you now can do that so easily if you learn a statistical computing language. It's the coolest thing in the world. So, all right, so we can do this on our simple program, so let's look at that. And just to make it come alive, because that's the whole point, making statistics come alive. All right. I mean, teaching it is to make it come alive. So let's look at this, and let's look at this exact situation here. And I want you to do it yourself and play around with it. And if you want to play around with this one, you just go to the grades right here, and then you go to regression, and you say, okay, let's predict finals here. And you can do it just from the homework if you want. That's what we did at first, and you saw that. And we click re-randomizations, and it immediately has 1,000 randomizations done. And there's our correlation coefficient of almost, on the previous page, of almost 0.4. It was 0.39 something, remember? And look how unlikely it is. That's a signal. That's a clear signal. And we reject the null that says there's no signal. It's all noise. All just noise. All just random. That's what we're trying to do here. Like, you don't need to, when you worry about a p-value, so what's the p-value? Well, we didn't even get, after doing this 1,000 times, 1,000 scramblings of the final and the homework, did we get any R? No, let's try it, any R as big as our sample? No. So let's do it some more. Now watch this. So far we've gotten 0. So this is what we did last time. I just want to repeat it because it's just to make sure you understand this. Not yet. Takes a long time. Oh, there we go. Okay, so let's look. Can you see that we've got a tail extending out there? That means it's almost reaching. And we got that. It says, okay, what does that mean? That's the likelihood. We just got a sample that looked like ours, just a tiny bit, like right there. So we say, okay, that's our p-value. That's the probability that we'll get this under the null. And we can keep doing it and see if we get, and the more randomizations you do, you don't have to, we have the whole population. So if you were a fancy math person, and you could analytically get this probability density function, right? That's probably what you could do if you take your higher, and if you did that and went through all the trouble, it's hard. You have a real population here, right? So you can actually get this function, right? And you could do that, and you could spend but takes you a few seconds, and you're going to, in the limit, it's going to be the same thing. See, I've done, 100, by the time it's going to be the same thing. So that's why I'm saying you don't have to waste your time on all these calculations. You can think about the real issues and solve problems. That's why statistics is extraordinary. When it's hooked up with computer science, it's taken the smartest, it's taken everything good about how we can think. Computers can never figure out the best probability models. They're going to match some situation. That's a human problem. That's what humans can do. They can think about what they know everything about the situation. They can think, oh, what is random in this situation that we want to solve? That's what we want to know. What is the random element that we can model? And you can try all different models, and then you have the computer do the calculations for you. So it's hooking up your intelligence, human intelligence, with computer intelligence to just be extraordinary. That's the idea. So here's a little baby version of it, and if you get this idea, you can go on and do it on your own. That's what statistics is all about. So, let's go to the next one. All right, you got this now. So now we're going to add another variable. So this time we're going to add exams, all right? So we're going to do the same thing. Let's look at it. We've got this huge signal out here. We've put exams into the mix. Do you think what we're testing here is something ridiculously stupid in a way, if you think about it. We're testing whether knowing your exams and your homework has any predictive value rather than just in determining what your final score is going to be. Better than just randomly assigning, like at the end of the semester, if I just randomly assign somebody else's final to you. How good a prediction could you make from your actual homework and exam scores if I just randomly assign somebody else's final to you? That's what this is saying. And it's saying that our final scores and the model that we came up with that it's no better than that, just due to random chance. We happen to, just by the luck of the draw, get a very correlated sample, a randomization. So we'll do it again. Let's do lots of them. I don't think it's going to take us forever to get, let's see. We'll keep doing it. I don't think this is going to change. Because look at this, the correlation is just too big. So it's going to get smoother, though. See how smooth it is? So that's the idea. Any questions? All right. So let's go, and now we're just going to do ANOVA. The last section is on ANOVA. So this is the same thing. So this is our, right here, we've got an R equal to 0.6198, and that's our observed sample R. And we're looking at how far this is from what we'd expect under the null. What we'd expect, but it's the empirical sampling distribution that we created, that we simulated. And you can see our signal is very strong, that we're going to reject. We are going to reject that this, our observed sample, is just that this difference from what we expect of R equals 0 is just due to the luck of the draw. Yeah, it could be, but look at the likelihood. We haven't, it's 0. At this point, we haven't seen any sample that's as big as that correlation, any sample R. Okay, so that's the idea. Now, last section before the exam is ANOVA. And it's ANOVA for comparing group means. All right. So, back in Stat 100, we tested hypothesis comparing the averages of two populations, right? Using the two-sample z-test, or t-test. And the usual null was that the population averages were equal. So our test stats was just the observed difference between the group means minus the expected of 0 over our standard error for the difference, where the standard error for the difference was the square root of the sum of the squared differences. And here's how we did the t-test. Very similar, we just tweaked it a little bit. And but what we did was, this is a number, right? Our observed difference. It's a number, and it can be, we're just looking at two groups. For example, if we were looking at, let's say, I wanted to test whether males or females, well, there's a significant difference in Stat 200 between male exam scores and female exam scores, let's say, or between the final score, how well males and females do in this course. Okay? So I'd look at your overall averages between males and females, and there's bound to be some difference, right? They're not going to be exactly the same. There's going to be a difference due to random variation. So what these Z and T tests did was said how likely that observed difference that we see is due to, when we did its test on that, is just due to the luck of the draw. In other words, how does it compare to the standard error here of the typical variation you see just due to random draws from a wider population? All right? And if we were going to do a re-randomization test, it would just be how likely that a difference that we see, let's say the difference was 2 percentage points, let's say the average was like 80 versus 82 or something, how likely it would be to get that big a difference just by randomly putting all your scores together and randomly dividing them into two groups and randomly doing that assignment between boys, and just see how likely a division of 2 points arises just through, how likely a 2-point difference arises just through random divisions. All right? But now what if we wanted to compare 3 or more groups? Like, let's say there was a significant number of trans people in here, so now we have 3 sexes. And we can't boil down the difference between the groups into a single sign number. We're looking at the difference between trans and boys, trans and girls, trans boys and, how can we do that? So, you can't assess a pattern of differences with a single number. So instead, that's where chi-squared and f-tests come in. We square the differences. We look at the sum of the squared differences. And we get the ratio of 2 variances, basically. That's what we did with the f-test. And we're going to do exactly the same thing here. It's just like what we did for multiple regression before, when we had to assess whether a whole collection of slopes were significant. We couldn't boil it down to a single number. All right, so we're going to do exactly the same thing that we did before. So this shouldn't take us long. We're just going to break up the variation of the y into 2 parts. All right, so what does that mean? So before, we always say sum of squares total, just how spread out those final scores are from the mean. The sum of the squared differences from the mean. If they're all exactly the same, we'd have nothing to predict. It's your spread of your finals, right? That's what we did before. And we said, okay, and then we said the variation explained by the model, by whatever we're predicting final scores from homework and exams, that would be our model. And then the variation missed by the model, all our observed minus predicted errors, all those errors, what we missed. And that would be the sum of the squares error. And that's what we broke it down into those 2 parts, right? And then we compared the average, the mean square model, the ratio of the mean square model, which is a variance because it's the sum of squared differences, to the mean squared errors. and we got an F stat. We're going to do exactly the same thing. All right, so let's just look at the difference. So here, for the regression line, as I just said, we have the sum of squares total, variation predicted by the regression line. That's the sum of squares model. Some people call it sum of squares regression. It's all the same thing. It's how well your model is predicting the variation in the y's, and then what's left in the error, which would be the scatter around the regression line, right? So now what are we doing? In comparing averages, what does this boil down to? So it boils down to looking at that same, we have a quantitative y variable. We're predicting finals still, so we have that same sum of squares total, but now we're not predicting it with a continuous quantitative variable, with a quantitative variable, like exams and homework. We're predicting it by a category, males, females, or trans, right? By a category. And what does that mean to predict it by a category? And what would be my best prediction for a guy? It would be the average of the guys. What would be my best prediction for a female? If you're just looking at categories, well, the average of the female. For trans, the average of the trans. So you're just looking at basically, you're predicting by group means. So what you're doing, I mean, the word we usually use in ordinary language is stereotyping. You're saying, okay, you fall into that category, you're a girl, my best prediction is you're going to do like girls do and ignore everything else, that you're just doing it by the group mean. And if you're a boy, etc. So this is another way of looking at ANOVA, is just how well stereotyping is doing those stereotypes better than just complete random, than just predicting an average for everyone. Okay? Than just saying, okay, does knowing your group membership, just knowing whatever group you're in, help me in predicting some quantitative variable like finals? Can I make a better prediction using knowing that than knowing nothing? That's all we're testing here right now. Okay? So, predicted by the group means sum of squares between plus sum of squares within. All right. So what do I mean? This is the variation. So let's look at this. So this says, okay, me being a female or you being a male, whatever, that I think I'm just going to group you with all the other people like you, all the other males, and predict your final score from them. But then, so that's the model, the strength of the model, if I do a good job doing it. But then there's, what's our error? Well, that's the scatter around that mean. So let's say there's a huge scatter. There's a huge spread among the boys. Let's say all the boys do exactly the same. Well, of course, then I should group you with the boys. Makes a perfect prediction. So if all the boys did exactly the same, then, and all the girls did the same, and well, then you'd have a perfect model. It would be like it would be exactly like no scatter around the regression line. It would be all the points fall in the line. All of people fall exactly, there's no difference between them. All the individuals in a group are exactly the same on that quantitative variable. And the scatter within is, okay, there's just too much individual variation within the groups to be able to, this overwhelms that, to be able to make a good prediction. So it's the scatter around the group mean. The boys are not all doing the same. There's a huge range. So it would be stupid or it wouldn't be a good predictive model to just use the group average for a boy. All right, so that's what we're doing here. And so the ratio of two variances, it's exactly the same thing. It's just a very simple model. ANOVA is so much easier in this context with comparing group means than what we've been doing. And this is usually taught at the Stat 100 level, or often, because it's easy. It's just, you just have these few categories and you're just making a prediction based on them, on their means. And it's much easier. But it's the same idea. So we're going to compute this F statistic, or for large N chi-squared, and it's going to look just exactly the same way. And, all right, let's just do an example. All right, so, and this is a super boring example. The only reason I'm doing this example is to show you exactly how to compute the sum of squares total, sum of squares mean, and sum of squares error, exactly analogous. In fact, we should probably compare it to what we did back in chapter 11. So this example matches up with this. But instead of having this continuous variable of exams, I just have a few groups. And it's exactly the same thing as this picture. So we can do it. And not this picture. Now I'm going to give you like 3. Here I gave you what? 3, just a few points here. Remember this example? I just gave you a few points here. I gave you what? Just 3 points. Well, now I'm just going to give you 3 groups. And we're going to do the same exact thing and go through these calculations again, which is probably helpful to you because we have to do this on the exam. So these are exactly the same thing we're going to be doing, except here the sum of squares total is exactly the same. This part's the same. The sum of squares model is just going to be, instead of having a line, you're just going to have group averages. And then the error, instead of the scatter around the line, will just be the scatter around the group average. So let's do it. All right. So I made up this example because I wanted to, first of all, compare an example where, well, you'll see. All right. So 2 experiments were done to test the effect of 3 drugs. So we have 3 drugs, drug A, drug B, and drug C. All right, and this is one experiment testing whether any of these drugs are different than each other. Any one works better or worse. And here's drug A, drug B, and drug C. These are results from 2 different experiments. Okay, so 3 subjects in each experiment. All right, and what was I doing? The null is that the 3 drugs have this equal effects, meaning their means are the same, all right, in the population. And the difference you see in the sample means, like here is a mean of 1. These 3 people averaged out to 1. These 3 people, what is this y variable here? Did I say? We're comparing 3 means because we're measuring quantitative responses to the drug, like duration of illness, not whether or not someone died. So for each of these, with this ANOVA, you're measuring some quantitative response. So maybe like how long, some measure, maybe some scale, some measure here of whether the drug worked. All right? A quantitative measure. And so here the group mean was 1. Here the group mean was 2. And here on this quantitative measure, the group mean was -3. So these means are very different. Right? And same in this experiment. We got the same means. 1, 2, and -3. So we didn't get the same means. But we want to know whether in the population they're the same, and these are just due to random variation. Okay, these differences between 1, 2, and -3, 1, 2, and -3, were just due to random variation. That's the alternative. At least one of the that's the null, and the alternative is at least one of the drugs is really different in the population. All right, so now what I want you to do, we're going to pull out our eye clickers, so because I want you to just do this intuitively. I want you to look at these, pretend these were really the results, okay? And you were testing these, maybe it was a drug, you only had a population of 3 for each one of them, okay? And it's to test, this happens sometimes because you're testing some rare disease or whatever, and you just want to see what happens when you give these. You might not have a very big population. So you're giving these 3 drugs, and you only have a sample of 3 in each one. Now pretend you actually got these results, and your only question is, do you think these drugs are equal? Do you think these 3 drugs are equal, or do you think one's different? Like if you prescribe it, it's going to have different effects on me. Or you got these results. These results. So you had 9 subjects, and you got these results. These are the 9 results on how well this drug worked. So you got all these results, or you got these 9 results. Okay? Now, why I'm comparing them, the means are the same. Go in both experiments. So the between the model, how different these means are, well, that's the same effect. But look at the other effect. Look how these are widely spread out around their means, and these are super narrowly spread out. So in which experiment, this will be does it look like stronger evidence to reject the null and think one of these drugs is different, at least, that they're not all the same in the population? Which does experiment 1 or experiment 2 have stronger evidence, okay, to reject that null? So let's go here and let's pull that question up. Okay, and here we have it. Whoops. And I'll start this. So, this is just, I just want you to, just get a feel, just a visual gut level feel for what's going on with analysis of variance here. Okay, so sorry about this. Ignore this. I see there's a experiment 1 has stronger evidence for the alternative, that at least one of the drugs is different. Experiment 2 has stronger evidence for the alternative, that at least one of the drugs is different. And both experiments yield the same evidence because they have the same means. So just vote, and when you're, let's see, I think, is everybody done with their voting? Okay. And I'll stop it at 1 minute, and let's look at what you said. 74% said 1. Okay, and that's right. Let's look at this, and why? Experiment 1 has stronger evidence. Why? Because look at your papers and experiment notebooks. The group C, can't you tell the group C is clearly different? Because it is much smaller with in-group error. So let's go to our document camera and look. What I'm talking about is this error inside here is much smaller. What is the error? The error is this. It's the spread around the group mean. So we're making a prediction. Our model for group A is 1 in both of them, right? We're going to predict 1. That's our, because it's the mean of the 3 people who took drug A. But you see how this is just a tiny little bit of error? I'm going to make it like, and this error is much bigger around the 1. See, this person, well, this person or this subject has no error, right? It landed, this person, but this has an error of 5, and this has an error of -5. Whereas here again, this person, I made up this data, and this person who scored 1 on this scale of how effective the drug was, then has no error, but the person who scored 1.5 has 0.5 error, and the person who scored 0.5 has -0.5 error. So these errors around here are huge. So can't you see that that we're more sure that people in group C are clearly different than these two groups? There's a little bit of overlap here, but when you look at these, there's a lot of overlap. I mean, look, this person and this person could have been part of group A. There's just a lot of overlap between them. So it's stronger in experiment 1, and that's what we're going to be measuring. The difference between, they both have the same between group means, but this has a lot more error. Scatter around, think of it as scatter around our predictions. So experiment 1 is stronger because C is clearly different. There's a lot more scatter in this one. Imagine, what if there was no scatter and all 3 people scored right at -3 here? All scored the group mean. Then we could make a perfect prediction based on these 3, and we'd think we had really strong evidence, right? And think about if these were really spread out, like hugely, you'd have no evidence here. The noise would completely outweigh the little differences between the groups. Whereas here, the differences between the groups is outweighing the noise. That's all analysis of variances. All right, so you look at the spread of the differences between the group means. How do the two experiments compare? Well, they're exactly the same. They have the same group means. What is the group means? A is equal to, the group mean is 1, group mean is equal to 2, and C is equal to -3 for both experiments. Those are our means. Okay, now look at the spread of the differences within the groups. How do they compare? That's just what we were talking about. Experiment 1 has much smaller within group errors spread. And those are the errors. That's going to be the sum of squares within. Those are the errors. And they have the same sum of squares model. That's the between. So this is going to be the same, but this is going to be really different. So this is going to give you a much bigger F statistic. All right, so that's what we say here. The F statistic compares, this is sum of squares between. I'm going to write it that way. Sum of squares between and sum of squares within. Remember? Look at, that's like model over error. Okay. And so then what we say is, so the F stat compares the differences between the groups to the differences within the groups. It compares the amount of variation between groups to the amount of variation within groups. Under the no of no difference between the groups, we'd expect that ratio to be about 1, right? Because if the model didn't work any better than the error, we'd expect them to be the same after you weight them by their degrees of freedom, by how many points there are, how many groups there are, and how many points there are. If the F stat is significantly larger than 1, then we'll reject the null. How much larger depends on the degrees of freedom for both the numerator and the denominator. All right, think of it this way. So that's what F does. And imagine basically that they're both estimates of the same population. There's no differences in the group means, so the numerator and the denominator, the mean square between and the mean square within, are both estimates of the variation of a wider population. And you'd expect them to be 1. There's no difference in a wider population between them. But this is more how the re-randomization thinks of it. We're going to look at both and see how they compare. If we re-randomize, what would we do? Think about what we do if we had to think of a model to model this random variation. We'd think of, okay, let's take all 9 points and randomly divide them into 3 groups. If there's no difference between the 3 groups, then I would randomly assign these quantitative scores, how well they did, these numbers here. So I have 9 y values here, and I would randomly assign them to each, make a random division. So 3 to this group, randomly draw 3 to these, and what's left would be there. And then I would look at that over and over and over again and look at the likelihood that I'd get such a difference under the null. That's what you would do, and we'll do that. Okay, so I say it. The null treats all 9 observations as coming from the same group. Imagine putting the 9 tickets in a box, shaking them up, and then randomly dividing them into 3 groups. The means of the groups would differ by the luck of the draw, right? All individual responses would be governed by the same laws of chance, having nothing to do with their group membership. So there's no reason that individuals in the same group would be any more like each other than they are individuals in different groups. And that's another way of saying that you'd expect 1, a ratio of 1. So it's a very nice way to make sense of the F statistic. Much easier to understand, actually, than what we've been doing. Okay. Now, so here's our summary of all of that. And so the only thing that we have to figure out is what are our parameters here. Like ANOVA for comparing groups of means is an extension. Okay. The terms are slightly different. For regression, we had this. So I'm just looking at for regression and for ANOVA here. And what's different? Well, we already talked about the mean square between is like the mean square model. But what about the number of parameters? Look at this. Look what's replaced. Look at this. Do you see that the number of parameters is the same as the number of groups? So let's right here. That's what I'm saying. That's what we're doing here. So remember the number of parameters for regression were all the terms on the right, all the betas, including the intercept. Now it's all the groups. So so this right here, G minus 1, is going to match up with G minus 1 here. So that's the only difference. So let's go through and do this one example, this computational example. And I'm sorry, it's just, it's not fun to do these sums. That we're going to do exactly the same thing as this. And this wasn't fun. And now we have even more points. We have 9 points instead of 3. So bear with me. And maybe we should make it look like that. Let's do that. All right. I better put my glasses on then. So we're using these. All right. So let's just, for the null hypothesis, all group population means are the same. Another way to say that is that our y variable, what we're measuring, that quantitative variable, if all the group means are the same, we might as well just predict y, our predicted y variable, just by the overall average of all the y's. The average of those. Our x variable here doesn't appear. It's just what group you're in. So all these numbers are y's, right? That's our quantitative variable is y. It's the only one. So all these numbers here, we have 9 y's. And just our group mean is called the overall mean. Another phrase that's usually used is called the grand mean. So you take all your y-ops, all your quantitative measurements, and average them. And that is the grand mean here. Now, so your sum of squares total, the sum of squares total here would be what? The sum of squares total is going to be equal to your each individual y minus the overall y, right? So this would be 1.5 minus 0. This is, if you average all 9 points, I drew it to make it super easy, our grand mean is equal to 0 in this example that we're going to go through. Our grand mean is equal to 0. So all I'm going to do is take, for the sum of squares total, I can do it right here. I'm going to take sum of squares total. We might as well do it because that's what we have to fill in right here. The sum of squares total. And let's just go through it. What am I doing? I'm taking every point. So the first one is what? 1.5. And what am I subtracting off? It happens to be 0 here, but usually it's not. I just made the computations easy here. I subtracted off the overall mean. And I'm going to do that for all 9 points. Okay? So that's just what we always do. It's our first step towards taking a standard deviation. So we might as well do it. So we have 1.5 minus 0 squared. The next one would be 1 minus 0 squared, 0.5 minus 0 squared, dot, 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 dot. Do you want me to write it out? Not if you want me to write the whole thing out. Okay. Well, it won't take us long at all. The next one is 1 minus 0 squared plus 0.5 minus 0 squared. Those are these three. Now I'm going to group B. So I'm just going to take these 3 points, subtract their average. So 2.5 minus 0 squared plus 2 minus 0 squared plus 1.5 minus 0 squared. So these are our group A, these are our group B. Now I'm going down to group C. Now, negative 2.5 minus 0 squared. I'm putting in the minus 0 because I want you to, you're not always going to have 0 here. So that's our grand mean. Just make sure you know that, the overall mean of the 9. Okay? All right, now we have 2.5 minus 0, okay, plus negative 3 minus 0 squared, plus our last one, negative 3.5 minus 0 squared. All right, so as you recall, these are just, before we square them, these are deviations from the mean. So you should check, when you add them all up, of course, they should add to 0. That's why we're squaring them, because we'd always get 0 otherwise. All right? So we do all that, and when I did all that, I got 43.5. So that goes right in here. So this whole thing is 43.5. That whole thing is, let's write that, 43.5 is what we got. All right, now we're going to break it up into two parts. So let's see what this is. So the sum of squares model, which is the sum of squares between, what are we doing here? Now, what is our model? Remember what our model is. Our model is the group mean. So right here, that's our predicted. When it says this is our predicted y, well, we have 3 groups, so we're only going to have 3 predicted y's. Even though we have 9 points, we're only going to have 3 predicted y's, 1 for each group. Remember, we're predicting on group membership. So predicted y's, we'll have 3 of them. So this right here, it's our predicted, that's why it has a hat, predicted y's. And there's only going to be 3 of them because we have 3 groups. And here, we're saying how well our model does the prediction over just using the average. So what's the difference due to our model? How much, that's what this is. So this is our grand mean here. Okay? So I'll call it the grand mean. That's how you usually see it. I'm sorry, I should do that here too. Here's our grand mean. That's 0 in our case. Grand mean. And this, what is just y sub I? Those are all 9 observations. Those are our observed y's. So these are our 9 observed y's. I mean, for this example, you might want to put in 9 observed y's, 3 predicted y's, and there's 1 grand mean. Just so you remember. Match it up to this example. All right. So now, but we're going to sum over all 9 numbers from I. We're going to sum over from I equals 1 to 9. All 9 numbers. So everything from group A is going to have the same predicted, everything from group B. You can see. Now what's this? This is our sum of squares error. And this one is just the observed, the 9 observed y's. Each observed y, how far it is away from its predicted y, minus the 9, not the 9 predicted y's, the what? 3 predicted y's. Okay, so that's what we're going to do. Now we've done this one, now we're on this one. Questions so far? Okay, so we're on this one, so we're just going to do that. And let's do it. That's the model. Okay, so the sum of squares between, that's right, sum of squares between. Okay, so let's look. For 1.5, it has a predicted y. What is the, okay, so everybody, not 1 point, everybody in group A is going to have the same predicted y. What is that? The average. Do you see that? That if you're in group A, our prediction, our model predicts stereotyping. Group A, I don't care what you are like, we're going to just say, the model says you're all alike, right? That we can make, our best prediction is just giving all the points in here the mean. We're not looking at anything else. So that's what we're doing. So for this point, even though it says 1.5, all 3 members in there are going to get the same predicted mean, predicted, there's only 3 predictions. So they're all going to get 1 minus the average. So they're all going to get 1. Okay? Because we're summing for all the points. We gave them that prediction. That was for group A. Now, how about for group, what are you going to get for group B? They're all going to get what? What are they going to get? Hello? You know, what should I write here? Tell me. 2, thank you. They're all going to get 2. And how about for the last group? What are they all going to get? -3. Okay, now if we added these up together, what do we have? Another way to write this would be 3 times what? 1 squared plus 3 times 2 squared plus 3 times -3 squared. So what does that give us? 9 times 3 is 27 plus, whoops, I didn't do this right, 2 squared. Right? So here we have 27, and there we have plus 3, and here we have plus 3 plus 12. So that gives us 42. So this is equal to 42. Whoops, that's in the model. Now, do you know what the error has to be? Before I even write it down, what do you think it has to be? 1.5. And then we'll write it down. But before we do and get lost in these calculations, let's draw our picture and match it up to, I said I would. So what is the sum of squares? What are we doing here? Let's remember. So which portion here is our model? And which portion, let's make it the same way so you can look back at our other one so you can see how it matches up. That was in chapter 11, and we drew that little picture, and, hold on, sorry. There it is. All right, so this picture. This picture, what was it? Our model, we drew it in blue, and it's how far, the difference between our model prediction and our just estimating the average for all the y's. And here this one fell right on, so it had no model prediction. So this was for this point, 1, 2 here. So this is our model, and this is our error. This is all error, and here was our model and our error. Okay, let's do the same thing here. And our model, I think it's easy. So let's see. Whoa, this one's really easy. Look how good our model does. All that distance. Probably easy, it's all that is model, and error is what? Our observed minus our predicted, just this little bit off. And here, our model so far, what did we have? We have 2 here, 2 minus, these are all 2 minus zeros, and these are all 1 minus zeros. So that's what that model is. All right, so let's do the model here, and this model here. So far, those are models. Actually, before I put the errors in, let's do the errors, and then we'll put them in. I showed it's the scatter around the model. All right? So do you see here what it would be? Let's do it. Because it's so little there, and maybe you'll understand it better if we just do it. Sum of squares within. Okay, so let's look back up here, and we say it's our observed y's minus the predicted for each one. For all 9 points. So let's go here, and our observed is 1.5, our predicted is 1. So that's going to be 1 minus 1, our observed is 1.5 minus our predicted is 1. So that's our first little error squared. And what's our next little error squared? Our next is, our next point was 1, and we predicted 1, so that has 0 error. And then our last one for group A is little errors here is 0.5 minus its predicted. So this one is 0.5 squared, this one's 0 squared, and this one's negative 0.5 squared. And let's just look at them up here, and we can see them. What are we doing here? Probably can't even see these points. Okay, so this is the one, our prediction, right? So this person, I'll make it in yellow, got just 0.5 off. That's what that one is. Somebody, this landed right at 1, so there's no prediction error. And this last one is below, so it's negative 0.5, but we're squaring it. So altogether, we've got that, okay? Can you see that? All right, let's go to our next one, and we'll just do all of them. And the next one is, probably you can see it's the same thing. Now we're going to look at, see this little piece of error from, we're looking at the predicted is 2. So we're just going to have 2.5 minus 2. So that's 0.5 again. And when we square it, and our next one, I drew it very symmetrical. It's not always this way. Our next one is 2. This is our observed minus our predicted. So this one, we got a perfect prediction for. 2 minus 2 is 0. So that's plus 0 squared. And our last one is 0.5 below. It's 1.5 minus 2 squared, which is negative 0.5 squared. So what I did is this little bit of scatter around here. Now your homework is going to, let's finish it up, and then I'll show you what your homework is going to look like. You're going to do the same thing with this one. And you can see you're going to have much, much bigger errors. Look at that difference. Your model is going to be the same. It's on a different scale, but here's your model. Your group mean is still 1. So your model's still going to be 1. But look at this error. It's 5 instead of 0.5. I made it 10 times as big. And here's your model's going to be the same, the 2. But now you have an error of 5 going this way and 5 going that way. And here your model's going to be still 3, right? And your model's just your distance from the overall. But your errors are huge here, much bigger. Okay? And so this is why you visually saw, when you looked at, you saw the ratio of the blue to the yellow, and you said, yeah, stronger evidence. Whereas here, the ratio of the blue to the yellow, don't have much evidence. This is what you're going to do. You're going to do for homework. You'll compute the F-stat. We're almost done. We're going to compute our F-stat in here from scratch. All right, so now we have our last, we didn't do this one yet. Okay, so now we're just looking at those yellow, and you can see the yellows are the same everywhere. It's just the 0.5s and the 0, right? So we have the same thing, and we're going to have 2.5. You have to be a little careful here because it's minus negative. It's negative 2.5 minus negative 3. You can see it's a distance of 0.5 squared, so that's 0.5 squared. The next one's just right at there. Can I just say 0 squared plus 0.5 squared because I'm running out of room? Does everybody understand this is just going to be negative 3 minus negative 3? Or right here, this is negative 3. And so there's no error. And the last one's going to be negative 3.5 minus negative 3, which is just negative 0.5, and you're going to square it. It's exactly the same thing. This will be a negative. All right, so now we can add these up, and what do we get? We get 0.5 squared plus 0.5 squared. So we get, here we get 0.25. This adds up to 0.5. This adds up to 0.5. This adds up to 0.5, and we check. We get the 1.5. Yay. All right. I know it's tedious. Please don't get lost in it. Look at the picture. You have little errors, and they're all the same. Here, your homework, you can have bigger ones. All right, now let's do our degrees of freedom. Remember our degrees of freedom, what the degrees of freedom are. So they are the number of groups minus 1 for the, first of all, the total is still n minus 1, so we have 8 degrees of freedom, n minus 1. Now, usually, for the error, for the model, we have p minus 1, but here it's g minus 1, so we have 3 minus 1, which is 2, 3 groups minus 1. And here we usually, you know it's going to be 6, and it's n minus g. Now we do the usual thing. We're just going to, I know, don't worry if you don't, it's all, you have it all right here. This is all we're doing, so it's all spelled out there. All right, so now we want the mean square, so we're just going to say 42 divided by 2, and that's equal to 21. We're going to say 1.56, we're just dividing by its degrees of freedom. 1.5 divided by 6, so that's 0.25. Now look at the ratio of those two. That's going to be big. That's our F statistic, the mean square model over the mean square error. And it's 21 over 0.25, which is 84. That's really big statistics, so you're going to reject the null for sure. Now, the standard deviation of the errors is often asked, so that's the square root of the mean square here. So right there, so you get the typical error is 0.5. Right here, the mean square errors, and that makes sense. Look at our errors. And r squared, what is r squared? Do you know how to get r squared from here? Would you know how to do that? How can you remember? If you forget, do you remember this? That the model, this is the sum of squares total, and it's divided up into two pieces. This is r squared and 1 minus r squared, right? Right? So we're dividing that sum of squares total into two pieces. So you just want the means, the sum of squares. So the question is, what is r squared? Well, we know that r squared times SST equals 42, right? So the model, we're just going to divide it, 42, this is the proportion, 42 divided by 43.5 is r squared. All right, the proportion that's due to the model of this total variation, that's the part that's in the model, and part that's in 1 minus r squared is that. You put 1.5 over that. So that's that in a nutshell, and I just wish that we had a little more time, but because in the last 5 minutes, I'm just going to do, now, you see how much time this is? When you have to do things from scratch and you kind of lose track of where you are. So what I wanted to say is let's just use this relationship of R that we've been doing the same thing and analyze some real data where we couldn't possibly do it from scratch because we have 858 students. And I'm sorry we're going to go the whole time, but this won't take us very long at all. So let's take a deep breath, and then we'll almost be done with analysis of variance, and you'll be more prepared for the exam. I posted all the homework. I posted the practice tests because I want you to have this weekend to study as much as you can. So let's go through this, and let's do it. And you'll be shocked at how little time it takes because we're not doing all those little minute calculations. So this is really interesting Stat 100 data from 2014. When the question of, do you believe, on a scale of 1 to 10, rate where you fall. 0 means you strongly favor gay marriage. This was before it was legal. And 10 means you strongly oppose gay marriage. All right? This was asked of all the Stat 100 students. And there are 858 responses. And I was wondering whether differences based on ethnic group were significant or not. Now, overall, the Stat 100 students are very liberal. They all choose pretty much, look at these spikes at 0. That means, yeah, totally in favor of gay marriage with all the groups. But when you take their group averages, they're quite different. And I was looking at them and I was saying, are there significant group differences? For example, this group, and it wasn't what I thought at all, so I had no idea. It was a perfect test of, I have no idea here. I wasn't going to pick out any particular ones. And this one was the lowest. I noticed that this is the highest. So I said, And I looked at, this was blacks and this was Hispanics. All right? So I'm just wondering, I'll do an overall regression test. And yes, raise your hand. Yeah? Oh, I just got r squared because I said, can I show you like just individually right afterwards? Okay? Because I just want to get on with this example. All right? And I'll put it on the video too. Okay. So we got that. And now, and we got this correlation right here. All right? So now, can we predict a random person's average towards gay marriage better by using these group averages than we can by the overall average? All right. So the first question I ask right here is, what's the appropriate significance test? And right away, because we have more than one group, two groups, you can cross off your Z and your T. And we have a big sample size, so you could use either of these. And so your answer is just either 1 or 2. Now, what's the alternative? The null is all the group means are the same. The alternative is not that they're all different, but just at least one of them is different, right? That's the complement. Either they're all the same or at least one of them is different. So compute the chi-squared. So let's do that. And the chi-squared is just going to be r squared over 1 minus r squared times n. This is very easy, right? It's just going to be, you were given r squared, right? You're given r, so you just square that over 1 minus, and you multiply it by 858. And I got 32.84. That's a giant chi-squared. Now, how many degrees of freedom? We have to compare it to a chi-squared curve. Degrees of freedom is g minus 1, same as p minus 1, right? And that is 5 minus 1, which is 4. Okay? So we look at the chi-squared degrees test with 4 degrees of freedom, and I got 9 point. Okay, so this, I look at the critical value, right? So I'm going to look at the critical value with 4 degrees of freedom. So I go here, the critical value, I'll just tell you what I got because we're running out of time, and I got 9.49. That's so much bigger than 9.49, right? If you drew a curve, you'd say 9.49, and that's 5%, and we are way far to the right, so we would reject the null. And we do the same with the f-stat. Sorry if I'm rushing through this, but the r squared over 1 minus r squared. Now, instead of multiplying by n, you have to tweak it. And it's not n minus p, but n minus g, divided by not p minus 1, but g minus 1. So we have the same exact thing here, this g minus 1. And so now we get the same thing, 0.1920 squared over 1 minus 0.1920 squared times, what, 853, a little bit smaller, but the big difference here is 4. And this 4 is the same as this, and the same as the degrees of freedom in the numerator. And here's our degrees of freedom in the denominator. And you can do the same. I'll draw out, so the critical value that we have to look at for f is going to be this particular curve with these degrees of freedom. And I'll just draw a rough sketch of it, and it's going to look like this, right? And the critical value that I got was 2.382. So that's going to be way out on the tail, 2.382. But we got RF, that's our critical value. This is our 5%, right? And RF is way out here. RF is equal to 8 something, right? It's 8. RF is, oh, I didn't do it. RF is 8.16. 8.16. So do you think we reject the null? Do we reject the null? Look how far out we are. It's not due to random variation, it doesn't look like. So reject the null and conclude at least one of those groups is different. And next time we're going to look at which one's different. And now, let's just, in the last 5 minutes, 2 minutes, you asked me, how did I get, so what do you know? you know the sum of squares, you know that the sum of squares model is equal to r squared times SST, right? Don't you know that? Don't you know the sum of squares model and the sum of squares error is equal to 1 minus r squared times, is this to answer your question in the back? So you're just solving here for r squared. So r squared is equal to sum of squares model over sum of squares total. So, hey, blonde girl in the back, hello, this is your question answered. Sum of squares model, you know this, is r squared times sum of squares total. And sum of squares error is equal, you know this, right? Don't you know that? All right, so how did I get r squared? I just divided both sides by SST. That's all. Okay, see you guys.